Hello.
Yes. Priya, sir is with us. You can start the session.
Okay, sir.
Priya, kindly
Yes.
start the session.
Yes, good morning to all the respected present here. I, Engineer Priya Mittal, Assistant Professor, Department of Civil Engineering, BFCET, welcomes you all on the second day of 1 week online faculty development program sponsored by AICET IST on recent developments in AI and robotics. Now, I would like to welcome our today's second speaker, Dr. Parvinder Singh, Assistant Professor in Department of Computer Science at Centre University Punjab Bathinda. He completed his BTech in Information Technology from Government Engineering College, Ajmer, Rajasthan, and MTech from Centre University of Rajasthan. He has also received Institute Gold Medal during his Masters. He completed his PhD from IIT Jodhpur in Quantum Information Processing and Quantum Computing. His research interest or his areas of specialization is cryptography, information security, network security, quantum information processing, quantum computing, and quantum cryptography. He joined Centre University of Punjab as assistant professor in year 2020. He has published more than 15 papers in international conference and journals. On behalf of Baba Farid College of Engineering and Technology, we welcome you, sir, to speak over today's topic, quantum robotics. Thank you so much, sir.
Thank you, ma'am. Am I audible?
Yes, yes, sir.
Okay. So good morning to everybody. I hope you are safe and healthy. And I am Dr. Parvinder Singh, Assistant Professor in the Department of Computer Science and Technology at Central University of Punjab, Bathinda. First of all, I would like to thank respected Chairman Baba Farid Group of Institution, respected Principal Sir, HOD, and the organization committee for giving me this opportunity. I am glad to be with you today. It would be my pleasure to present before you. So, as we know, due to the farmer protest today, I could not reach to my university. So, from my village, I will continue. And there may be some weak internet signals. That's why the voice quality may be suffer. So, I am very sorry for that. And so, we start. So my topic is quantum robots in review structure and applications. I have designed my presentation in 5 different modules. In first module, domain of research, I will briefly describe the importance of quantum information and computation. And then I will explain the basic terminology and concept in introduction section required to understand the quantum robotics. In next section, I will briefly describe the quantum algorithm. With this, I will explain the basics of quantum machine learning and finally explain the quantum robotics. In this new era of technology, major research thrust areas are quantum information and computation, where we mainly concern with the fundamental aspect of the quantum information and the application. And in the view of mechanical engineering, new domain of research in quantum robotics. So the quantum robotics is the fusion of quantum theory and robotics, and use the quantum system to construct a new paradigm of robotics called quantum robots. The research in this area or in this new thrust area have been started early 1998 by the Benioff, who present the concept of quantum robotics in the perspective of physics. He also emphasized the application of quantum computer in the quantum robots. This is the first paper that changed the research interest towards the quantum robotics. So this paper is written by the Benioff in 1998. So at this point, it is important to understand why do we need quantum information and computation. So as we know, according to the Moore's law, the computer power will be doubled for the constant cost roughly once in every year. Therefore, the quantum mechanics become extremely important in the field of computer and information processing due to the imminent possibility that the current size of chips from micron will further reduce to near atomic dimension, where all processes are controlled by quantum mechanical phenomena. So the quantum information processing offer many potential applications for information transfer in terms of efficiency and secrecy that cannot be achieved using classical computations. In general, these applications are result of phenomena called quantum entanglement, a result of superposition principle in quantum mechanics that way ahead of the classical source due to the existence of quantum correlation between the entangled qubits. With this, the application of quantum technology in advancing the performance of mechanical system at macro scale are found in developing novel sensors and actuators. So this picture is showing an example of entangled robot, that are the quantum robots. So this picture shows the entangled robots. So the quantum computing is an interdisciplinary research area. So the quantum information and computation had emerged as interdisciplinary research area at the interface of diverse academic disciplines such as computer science, mathematics, physics, and engineering. So that quantum technology and robotics autonomy, two areas are brought together in establishing an interdisciplinary interface that contribute to advancing the field of system autonomy and pushes the engineering boundary beyond the existing techniques. So in order to understand the basic concept, let me first explain some basic terminology used in quantum information and computing. Hence, we start with what is the computing. So performing the arithmetic and logical operation is computing. And a computational machine, such as a calculator or computer, takes data as an input, performs some calculation or processing to convert this data into the information. For example, here 2 plus 2 is a data for the calculator, and it perform some calculation and give the information as the output, and this information is 4. Now, quantum computer is a machine that performs the calculation based on the law of quantum mechanics, which is the behavior of particles at subatomic level. So the quantum computers are based on the fundamentals rules of the quantum mechanics. The fundamental applications of quantum computing are in different areas such as in cryptography, in key exchange and communication. It will also use in fast database search, in artificial intelligence and machine learning. And the quantum computing are also important in the area of quantum robotics. We will not explore these applications in detail, but only about the quantum robotics. And this diagram show that integer factorization of a large number is not possible with the classical computing in finite polynomial time, but it is possible with the quantum computers. So there is a large prime number, and we cannot factorize it with the using the classical computer. But with using the quantum computer, we can easily factorize this number. So this is the advantage of quantum computer over the classical computer. Now, the fundamental unit for classical computation is bit. As we know, the bit is the fundamental unit of the information for classical computer. And the only possible value of the classical bit is either 0 or 1. So therefore, the state of classical computer is described by some long bit string of 0 and 1. And the quantum computation is built on the analogous concept of classical computation, known as a quantum bit or qubit. So the qubit is the fundamental unit of quantum computation, and it is a mathematical representation of a state of a system. The individual unit of a quantum information are qubit 0 and qubit 1. So qubit 0 and qubit 1 are represented in a cat-bra notation. Okay, in classical computer, we directly use 0 and 1 as a bit, but here we use a notation, cat-bra notation, for to represent the qubit 0 and qubit 1. Qubit 0 and qubit 1 are known as a computational basis. It can be represented as a two-dimensional column vector 1, 0 and 0, 1 respectively. The fundamental difference between bit and qubit is that the qubit can be represented in a linear superposition of qubit 0 and linear superposition of qubit 0 and qubit 1, such as a state psi can be represented as a alpha 0 plus beta 1. We can also represent qubit 0 as a spin down and qubit 1 as a spin up for physical representation of the qubit. And we know when we perform the measurement on classical bit, it will give either 0 or 1. The value of the bit is either 0 or 1. And if we try to measure the state psi of a qubit, it will either collapse to qubit 0 with probability alpha square, or state 1 with probability beta square. So if we perform the measurement on this state, it will either collapse to qubit 0 or to qubit 1 with different probabilities. The state vector describing a 2-qubit system can also be represented in a linear superposition of 4 basis states 0, 0, 0, 1, 1, 0 and 1, 1. As discussed, the superposition principle lead to quantum parallelism, which is the fundamental feature of many quantum algorithms. For example, Grover algorithm and Shor algorithm. So a classical register with n bit can have 2 to power n possible states. But at a given time of instance, a classical computer can store or process only one of the state from the set of possible state. For example, if n equal to 2, there have a combination 0, 0, 0, 1, 1, 0, and 1, 1. But at a time, we can only process one of these set of states. But a quantum register can be a superposition of all 2 to power n possible state. So due to the superposition, a quantum computer can process all the possible state simultaneously at a given time of instance. So we know we can write the different quantum state in a superposition. So a quantum computer can process all the states simultaneously. So this is provide a quantum parallelism. So quantum computer offer an exponential increase in computational speed and space with the given size of system over classical computer. So the as we know, the qubit represent the information and that can be transformed from one form to another form using quantum gates. As we know, in classical computing, we use some different gates such as NOT gate, AND gate, OR gate, NAND gate. Similarly, in quantum computer, there have a number of gates. So I am going to specify some important single and two qubit gates. These gates are reversible in nature. So first one to consider is X gate, which is quantum analogous of the classical NOT gate. It acts on the state such as A00 plus B11, flip the computational basis. That means it takes 0 to 1 and 1 to 0. So here 0 is converted into 1 and 1 is converted into 0. So X gate is a analogous concept of classical NOT gate. And this gate also represented by a 2 cross 2 unitary matrix 0, 1, 1, 0. Another important gates are Z gates and Hadamard gate. Where Z gate acts on a state, it leaves the state 0 unchanged but flip the sign of 1, such as A0 plus B1 is changed into A0 minus B1. So qubit 0 is unchanged, but the sign of qubit 1 is changed to minus. Where the Hadamard gates take 0 to 0 plus 1 by root 2 and convert 1 into 0 minus 1 by root 2. An important 2 qubit gate is C NOT gate, also called as controlled NOT gate. It has two input, known as control qubit and target qubit. If control qubit set to 0, the target qubit unchanged. And if control qubit set to 1, the target qubit is flipped. So it is a 2 qubit gate that is known as a control NOT gate. There are many numbers of gates in quantum computing, but we mainly discussed or use these four type of gates in our computing circuits. We have already seen how to represent a single or 2 qubit state as a linear superposition of basis state. Therefore, n qubit state can also be represented as a linear superposition of 2 to power n basis state. I will now discuss how do we distinguish between two states. All quantum states can be categorized into two different categories, a sample, namely pure state and mixed state. And the mixed state can also be represented by a density operator rho as a convex combination of pure states such as P1, psi1 plus P2, psi2, psi2. This is the probability when the system in state psi1. P2 is a probability when the system or system state in psi2. Algebraically, if the trace of square of density operator is equal to 1, then it is considered as a pure state. And if it is less than 1, then it is considered as a mixed state. Now we discuss about the Bell inequality and entanglement. So the debate that these states having important and strange property started as early as in 1935. When Einstein, Podolsky, and Rosen write a question on the completeness of quantum mechanics as a physical theory using the formalization of locality and reality. And motivated by their argument, John Bell derived an inequality whose violation confirmed the existence of non-local correlation between the quantum particles. And the state which maximally violate this inequality are known as maximally entangled states. So John Bell derived this inequality, and if any system or quantum state violates this inequality, then it is entangled state. So the violation of Bell inequality confirms the existence of non-local correlation in the system. And a quantum resource having non-local correlation can be used to achieve the information processing task. Those are more difficult or impossible with classical resources. This plot here show a relationship between the state parameter theta of a pure state psi sine theta 0 plus cos theta 1 and the Bell CHS operator. If theta is 0, state is satisfy this inequality, so it is a product state. And if theta is non-zero, state violates the inequality and attain a maximum value 2 root 2 for the maximally entangled state. So if any state violates this inequality, then this state having a non-local correlation. As we know that the state that violates the Bell's inequality are entangled state. So entanglement is a pure quantum mechanical phenomena with some interesting property such that measurement performed on one subsystem affect the measurement outcome of other subsystem. For example, if Alice and Bob are two users and they are very far from each other and they share a entangled state. So when we perform the measurement on Alice qubit, and if the measurement outcome is 0, then without measuring or without performing any measurement on the Bob qubit, we can find the measurement outcome of Bob qubit. That will be 1. So if the Alice measurement outcome is 1, then the Bob measurement outcome will be 0. So if we perform the measurement on Alice qubit and without measuring the Bob's qubit, we can find the result of measurement for Bob. So there may be a possible of the communication if the Alice and Bob are very far from each other without physically sending any information. So algebraically, if a state psi1 to cannot be written as tensor product of or a convex combination of tensor product of psi 1 and psi 2, then it is called as entangled state. For example, psi 1 2 is written as 1 upon my root 2 0 1 plus 1 0. This is a 2-qubit state that is maximally entangled state. So it cannot be written as a tensor product of subsystem. And as a counter example, we represent a psi 1 as a linear combination of basis state 0 0 0 1 1 0 and 1 1. But it can be written as a tensor product of phi 1 and phi 2. So this state is separable state, but this quantum state is entangled state. Now the effect of environment on the entanglement and non-locality. So the entangled system owing the non-local correlation between the qubit are very useful in quantum information and computing. However, degree of the entanglement or non-local correlation gets degraded once the entangled system interact with the environment. So this is a closed quantum system. There have no environment, and this is the open quantum system. There is a environment, effect of environment. So in general, when quantum state under go the decoherence, then the pure state evolve into mixed state. So if a pure state undergoes from the environment of, or if there have an environment effect, then this pure state is converted into mixed state, and the efficiency of computation also suffer. For example, if rho in ENV is the initial state of environment which interact with the state rho of the principal system, then the final state of the principal system is epsilon rho. So mathematically it can be represented as epsilon rho is equal to summation over k ek rho ek dagger, where operator ek are known as operational element for the quantum operation. So with this, we have completed basic terminology and concept used in quantum computing. Now we come to the quantum algorithm. So the quantum computers are designed to outperform standard computer by running the quantum algorithm. So the quantum algorithm that run on the quantum computer and achieve a speed up or other efficiency improvement over the possible classical algorithm. So quantum algorithm offer an increase in computational speed and space with the size of system over the classical algorithm. Computational problems are classified under the subject of computational complexity theory, and based on the hardness of problem solution, a complexity class contains a set of problems. Those have some common feature with respect to the computational resources needed to solve these problems. For example, if a problem can be solved in polynomial time using the deterministic classical computer, then this problem is in class P. If a problem can be solved in polynomial time using a probabilistic classical computer, then this problem belongs from the complexity class BPP. A complexity class of quantum computation is BQP, which contain all computational problems which can be solved efficiently using the quantum computer. And if the solution of a problem can be verified in polynomial time by a deterministic classical computer, then the problem belongs to the NP. And if the solution can be verified in polynomial time by using the quantum computer, then this in under the QMA. So these are the different categories of the different problems. So when we design any quantum robotics, there have a different uh, problems such as a searching problem, optimization problem, and according to these problem, we specify the class of problem, and based on that, we can say the quantum computers are more useful than the classical computer. We will see in next upcoming slides. So these are some areas where the quantum algorithm are used, such as hidden subgroup problem and in cryptography. One of the most basic problem in computer science is unstructured search. That is also significant in robotics. So this problem is called as a search and optimization problem, and theoretical results show that the quantum robots can reduce the complexity of search problem from n squared in classical robots to the n root n in quantum robots using the Grover algorithm. So when we design a quantum robots, we use a Grover algorithm for searching. Next is the next application is the quantum simulation, quantum walks, and the zero qubit application. Now the one is the question from the audience whether they are whether these quantum computers are experimentally implemented or not. So this table show some proof of the experimental implementation of the quantum algorithm, such as Shor algorithm is implemented using the bulk optics to factorize the of it, number 21 in its prime factor 3 and 7. Similarly, the Grover algorithm is implemented using the NMR technology that is used for unstructured search of length n equal to 8 means 8 number can be searched in using the Grover algorithm, and it is implemented using the NMR technology. And similarly, these are another algorithms such as HHL algorithm, quantum handling. These are also implemented by using different techniques. Now we come to the quantum machine learning. So I will provide the brief introduction to the quantum machine learning. It is not a topic of today's discussion, but a brief knowledge is required to understand the quantum robotics. As we know, robot is a machine, and to train the machine from an algorithm to implement a specific task or to make a decision is called as machine learning. So the use of quantum phenomena, which we have discussed in previous slides, like superposition and entanglement to solve the problem in classical machine learning, pave the way of quantum machine learning. So there are a lot of quantum machine learning algorithms, such as in quantum clustering techniques, we use quantum Leloit algorithm to solve the key main clustering problem. Similarly, quantum neural network model is a technique of deep supervised learning to train the machine to classify data, recognize the pattern or image. It is a feed-forward network. The basic principle is to design the circuit with qubit. So the qubit are neurons in neural networks, and the gates, quantum gates, that are the polymetric rotational gates, are used as a weight. There have another technique which is called as a quantum decision tree that is used to classify the different classifier to classify the different data or images. This table shows literature review for the different algorithm of the quantum machine learning. For example, there is an algorithm K median. It is a reference for further reading, and it is implemented or based on the Grover search algorithm. It provides a quadratic speed up over the classical K median algorithm, and it is designed for the classical data. The generalization of the performance is still not calculated either numerically or analytically, and it is not implemented still. But we can see the neural network and the boosting algorithms are already implemented, and the generalization of the performance is also calculated analytically as well as numerically. So this table provide a basic literature review of the quantum machine learning algorithms. Now we come to the main topics of today's talk, which is quantum robotics. So from the development trend of robots, there are two important research areas. First, increasing the robot intelligence and reducing the physical side of robot. The key to increase the robot intelligence lies in improving the performance of sensor and increasing the speed of learning and decision making. At the same time, the reduction of physical size of robot will cause quantum effect to become more prominent. So there are two major categories of the quantum robots. In first category, mm, sorry, the principle of quantum mechanics and quantum computing and quantum algorithms are used to design a robots. And in second category, robots are designed or to implement the basic application of the quantum computing, such as teleportation and super dense coding, and to implement the fundamental principle of the quantum computing, such as entanglement. So the standardized definition of the quantum robot is a quantum robot is a mobile physical apparatus designed for using the quantum effect of the quantum system, which can sense the environment and its own state, process the quantum information, and accomplish meaningful tasks. Furthermore, the performance can be improved through equipping quantum robots with quantum sensor, and the speed of robot learning and behavior and decision making can be increased using parallel computing, such as quantum parallelism, fast searching, and efficient learning from the quantum algorithm. So this figure shows the block diagram for system structure of the quantum robots. So in any quantum robots, major part or components are, first is the MQCU, called as multi-quantum computing unit. Second is the QCU, quantum computing unit, quantum controller, actuators, information acquisition units, quantum sensors, and quantum bus. We will discuss about these units one by one in upcoming slides. So this is the basic structure for the quantum robots. So MQCU is the information processing center and act as cerebrum of a quantum robot. It receives tasks described in quantum language and exchange information with its environment via quantum sensor or external communication. As we know, there are a variety of information in robot development, such as task information, sensing information, environment information. So MQCU run the specific quantum algorithm in order to store, analyze, and compute this information to generate the indication signal for the quantum controller. MQCU generates some indication signal for the quantum controller that direct the actuator to perform certain operation. So it give a direction to the actuator to perform certain operation. QCU can exchange information with each other from rapidly and secretly than the control unit of classical robots. So the quantum control unit can communication with each other with speedily and secretly than the classical robots. The quantum, so MQCU is made up of many quantum computing unit called QCU, and each QCU accomplish some specific task and exchange the information with each other through the quantum bus. So the quantum bus may be a refreshable entangled resource. As we discussed a example of Alice and Bob, they share entangled resource. So quantum bus may be a entangled resource or some other quantum circuit. So the quantum bus can also perform the general function of classical bus such as PCI bus. Each quantum computing unit in quantum information processor, and it can perform some tasks such as quantum computing, storing the quantum storing the information in quantum memory, or the task description. So this is as a CPU in classical computer. Now we come to the quantum controller and actuators. These are the execution and control operators of the quantum robots. A quantum controller receive and process the indication signal from the MQCU. As we discussed in previous slide, MQCU provide a indication signal to the control quantum controller. So a quantum controller receive and process the indication signal from the MQCU and inform the actuator to carry out the corresponding action. It acts as a connection between MQCU and the armor actuator of the quantum robot. So it will work as a connection unit between the MQCU and the actuator. Usually a quantum controller is a quantum system such as a quantum C-Note gate. So this is a quantum circuit designed with the basic quantum gates. The actuator executes some action determined by the indication signal from the quantum controller. An actuator may be a pure quantum system or a semi-classical operator capable of processing quantum information. So actuator can be use the classical information as well as quantum information. So it is a semi-classical operator. Generally, the actuator can exchange quantum information as well as classical information with the quantum controller. And in some specific circumstance, actuator and quantum controller can be considered as a single operators, which can directly receive the information from the MQCU and carry out some action on its environment. So now now we come to the information activation unit. As with the classical robot, a quantum robot need to perceive its environment and acquire information through the information activation unit. So in a quantum robot, quantum sensor perceives the information of its environment. The robot may also receive some other information from the distant mainframe or another quantum robots through the external communication. The information may be acquired include quantum information and classical information. So quantum robots have communication interface to exchange information with distance mainframe or with other quantum robots, which can constitute a multi-quantum robot system. With external communication, quantum information can be exchanged, and the advantage of quantum communication, such as high channel capability, perfect security, and quantum teleportation, super dense coding, secret sharing, these can be utilized in communication. So the quantum bus is used to provide a quantum information as well as classical information between the different unit of the quantum robots. Finally, I provide a brief introduction about the quantum sensor. A quantum sensor is a kind of microstructure sensor, which is designed by applying the quantum effect. In order to detect the classical signal, there are two types of sensor, namely SQUID, superconduction quantum interface device, and quantum well Hall sensor. SQUID sensor are extremely sensitive magnetic sensor that are constructed based on the principle of superconductivity. So these sensors are based on the principle of superconductivity. SQUID sensor can convert changes in current or magnetic field to measurable voltage and can detect magnetic fields as small as 10 raised to power minus 10 Tesla. And quantum well Hall sensor are kind of high performance micro Hall sensor and use two-dimensional electron gases to obtain a compromise between high mobility and high carrier concentration while maintaining a reasonably high heat resistance. Quantum well Hall sensor can be used to detect electromagnetic field under the different circumstances due to the high sensitivity and good temperature stability of the quantum sensor. So can equip the present quantum robot with the sensor to measure extremely weak electromagnetic field. So in quantum robots, we can use both quantum sensor and the classical sensor. And if we use the quantum sensor in quantum robots, it provides the advantage such that sensor can measure extremely weak signals. So it will improve the efficiency of the quantum robots. So now we come to the different algorithms that are designed for the quantum robots. So a key aspect of a quantum robot design is development of a high efficiency learning control algorithm. As we know in classical robot, it is difficult to perform algorithm with high complexity while satisfying the requirement for real-time processing because the CPU cannot compute fast enough and the integration of chips is limited. So as just as classical robot, most planning and control problem of quantum robots can be posed as search problem. So we use the Grover algorithm for searching in quantum robots. So consider a robot planning system whose state evolve according to a certain transition probability that depend on the control U. If a robot is in state I and choose a control U according to the policy pi, it will move to the state J with probability Piju and a cost Giuj. Now suppose that the desirability of a state is defined as V, which means the value of a state. So it is based on the minimum cost and the next state that we want to come. So the task of a robot to planning system is to find out the optimal sequence of V state for unstructured search problem of the search space N. So there are unstructured searching, and when we use the classical computing for unstructured searching, there is a linear search, binary search, and if we use the linear search algorithm, then the computational complexity in classical computation is ON. So in robotics, it is an important task to search for the suitable action from the action space based on the current state of the robot. And if the complexity of state or action space is ON, then the overall complexity of the problem for classical robot is equal to n raised to power 2, because for searching there is a complexity n, and for action there is a complexity complexity is also n. So the overall complexity is n square. Whereas a quantum robots can reduce the complexity to O n raised to power n by using the Grover algorithm. Therefore, the quantum robots make a use of Grover search algorithm in to search the optimal sequence of the desired state. Now, as classical robot, the essence of robot learning is deal with the state action pair. So this is the state T and this is the action T. So we require a machine learning. So the learning method are generally classified into supervised, unsupervised, and reinforcement learning, as we discussed in previous slides in quantum machine learning. So the supervised learning require explicit feedback provided by the input output pair and give a map from input to output. That is a classification. And in unsupervised learning, only process on the input data. That is called a clustering in classical machine learning. However, reinforcement learning uses a scalar value named derivative to evaluate the input output pair and learn by the interaction with the environment through the trial and error. So quantum robots adapt a learning algorithm which is called as a quantum reinforcement learning, QRL. So that is inspired from the quantum superposition and quantum parallelism. So this is the table show the comparison between comparison of the time complexity between the classical robot and quantum robot with respect to the number of action. So this is the number of action. This row for the complexity of classical robot and this row for the complexity in quantum robots. So here we can see for 10 raised to power 2 actions, complexity of classical robot is 10 raised to power 6. And for classical robot, the complexity is 10 raised to power 5. And if the number of actions are 10 raised to power 8, then the complexity is 10 raised to power 12 and 10 raised to power 8 for classical and quantum robots respectively. So we can induce from more number of action, quantum robot is best choice. So this table shows the comparison between the classical robot and quantum robot, such as the system properties for the quantum robots are quantum system and for the classical robots these are mechanical system. Onboard sensors used in quantum robots are SQUID sensor and quantum Wellhall sensor, but in classical robot we use infrared sensor, ultrasonic sensor and CCD camera. The physical loads for the quantum robots are quantum mechanical load, and for classical robot there are a classical mechanical load. Information processing center is a MQCU, which is called a multi-quantum computing unit, but in classical robots we use the classical processor such as classical computer. The information types in quantum robots are both quantum information and classical information, and in classical robots the information is only classical information is used. The quantum robots are highly sensitive, but the classical robots are relatively lower sensitive. The physical size of the quantum robots is microcosmic, and in classical robot mostly micro. The technical difficulty, these are more difficult, and classical robots are easier in compared to the quantum robots. And the communication types in quantum robots, both communication, quantum communication and classical communication can be used in quantum robots, but in classical robot we used only classical communication. And due to the quantum parallelism, the quantum robots are very powerful parallel processing capability, but in classical computer, in compared to quantum robot, it is very weak. So before concluding my talk, I am very thankful to the Dong and et al. Um, that is a paper which is titled as Quantum Robot Structure Algorithm and Application, published in Archive. That is a very interesting paper to understand the basic structures of the quantum robot. This figure showed how robots can help to implement the quantum application such as teleportation, cryptography, and super dense coding. So this is the second type or second category of the quantum robots. So this figure display the practical implementation of the quantum cryptography. So there is a two user. First one is called as Alice and receiver is Bob. And there is a third party which is called as attacker or untrusted third party, Eve. These are some components such as ledger, polarizer rotator, beam splitter used for to experimentally implement the quantum cryptography. And for this diagram or the experimental setup of a quantum cryptography, there is a quantum cooperative ground robot. This robot for the Alice, and this for the Bob, and this robot is for Eve. And this show the practical implementation of the quantum cryptography. So I hope you enjoy this lecture and understand the basics of the quantum robots and basic quantum computing. So now we see a little documentary on the quantum computing and robots. Is my screen to visible to all?
Yes, sir. Yes, sir. It's visible.
Okay, okay. Voice is audible for video? Hello?
Yes, sir. Kindly start the video.
Okay.
Yes, yes. Audible.
In a world where everything is driven by computers and technology, how far can you imagine the great heights of artificial intelligence or quantum computing will go? In fact, none can think about the potential applications of both technologies. Both possess the power to be integrated with numerous mechanisms and add more efficiency and value to it. While everyone is still digesting the fact that robots with the integration of AI can actually be intelligent, quantum computing has also approached robotics to discover some new nuances. As we enter into a new era of computing, the paradigm shift will also impact the work of robotic scientists and the applications of robotics. According to a research report, Quantum Computation in Robotic Science and Applications by Bernhard Dieber, we acknowledge that the possibilities, as well as new approaches to known problems, will enable the creation of even more powerful and intelligent robots that make use of quantum computing cloud services or co-processors. The report throws light on potential application areas in quantum computing for robotics. As noted by the report authors, there is a high probability that quantum computers will have a positive impact on many scientific disciplines and their applications in the future. In several fields, useful applications are already being explored, including scientific computing, cryptography, chemistry, drug development, and finance. However, across the robotics field, the following are the significant applications of quantum computing. The modern autonomous robots need fast vision capabilities in order to perceive and assess their environment. Computer vision and image recognition algorithms are computationally expensive as they have to compute results on millions of pixels. Therefore, the hopes lie with the quantum efficiency to better understand the nature of visual information and to secure, store and process them efficiently with the help of quantum properties entanglement and parallelism. Such attempts lead to a sub-discipline called QIM, quantum image processing. The basic idea is that properties of an image, like the colors at certain positions, can be encoded as qubit lattices, which was widely accepted and formally extended by many representations and possible applications, including videos. As visualized into Kerr, quantum image representations, transformations, applications, and algorithms are required for robotic perception. However, this approach only deals with two-dimensional images, which is not sufficient when dealing with robotic perception, where the input of multiple sensors is often fused into a three-dimensional point cloud in order to locate and identify objects and environments. As suggested by the report, currently, only a few methods exist to express a three-dimensional image by quantum representation in the form of the quantum point cloud. As with other quantum technologies, the general expectation is that performance of its traditional equivalents by far. Traditional AI, in contrast to modern machine learning approaches, is based on formal knowledge representations, for example by rules and facts, and algorithms, in order to optimize the robot behavior or mimic intelligent behavior of humans. AI applications are frequently used in robotics, like path planning, the deduction of goal-oriented action plans, system diagnosis, the coordination of multiple agents, or reasoning and deduction of new knowledge. Most of these applications employ variations of uninformed, called also blind, or informed, called also heuristic, search algorithms, which are based on traversing trees or graphs, where each node represents a possible state in the search space, connected to further follow-up states. Whether it is complex search, basic search or graph search, quantum computing works as the alternative for AI in almost every aspect. For example, for graph search algorithms there is also a quantum alternative based on quantum random walks. Moreover, quantum algorithms for decision-making under uncertainty applications are already formulated, like quantum Markov chain and quantum Markov processes. For many years now, attempts have been made to solve classical robotic tasks using artificial intelligence methods as an alternative. For this reason, it is not surprising that analogous works can be found, which want to solve kinematic problems with quantum neural networks, e.g., the inverse kinematics problem, or using quantum genetic algorithm, for example for trajectory planning. The authors expect that the two levels of control in robotics, i.e. abstract task planning and specific movement planning, that are currently often solved separately due to their combined complexity, can be solved in a more integrative way through quantum computing. In particular, the potential of quantum optimization will provide interesting new opportunities for control schemes that utilize online optimization, such as model predictive control, or even classic dynamic programming formulations of control problems. Furthermore, the use of quantum computers in a multi-state operation appears to be useful to find the global solution of complex optimization problems. For this purpose, a first quantum computer resource for the generation of start solutions and a second quantum computer resource for the finding of optimal solutions are used. In modern robotics, experience shows that even carefully designed and manufactured robots encounter faults due to reasons like degradation of components over time or incomplete knowledge of the environment in which a robot operates. Therefore, methods to detect and specify these faults are essential. The problem of diagnosis can generally be characterized as the problem of finding the components in a system that describes the discrepancy between the observed and the expected behavior of the system best. The set of methods builds either on systems theory, AI methodologies or hybrid approaches. The classic consistency-based approach, for example, deduces diagnosis on the basis of solving a minimal hitting set problem, which is a common optimization problem in AI. The hitting set problem is one of the 21 classical NP hard problems of CARP. It can be reformulated as a vertex cover problem for which quantum computing approaches already exist. Data mining is the process of extracting information from and discovering patterns in large datasets. Thus, data mining is a valuable tool for knowledge discovery in order to diagnose systems, e.g. to identify the sources and reasons for erroneous robot behavior by mining the robot's log files. Data mining and analysis involve methods from machine learning, statistics, and database systems, like index searches, which are optimally suited to be tackled with quantum algorithmic approaches.
Quantum computers use the natural world to produce machines with staggeringly powerful processing potential.
I think it's going to be the most important computing technology of this century, which we are really just about 1/5 into.
We could use quantum computers to simulate molecules to build new drugs and new materials, and to solve problems plaguing physicists for decades. Wall Street could use them to optimize portfolios, simulate economic forecasts, and for complex risk analysis. Quantum computing could also help scientists speed up discoveries in adjacent fields like machine learning and artificial intelligence. Amazon, Google, IBM, and Microsoft, plus a host of smaller companies such as Rigetti and D-Wave, are all betting big on quantum.
If you were a billionaire, how many of your billions would you give over for an extra 10 years of life? There are some simply astonishing financial opportunities in quantum computing. This is why there's so much interest, even though it's so far down the road.
But nothing is ever a sure thing, and dealing with the quirky nature of quantum physics creates some big hurdles for this nascent technology.
From the very beginning, it was, understood that building a useful quantum computer was going to be a staggeringly hard engineering problem, if it was even possible at all. Right? And there were even distinguished physicists in the 90s who said this will never work.
Is quantum truly the next big thing in computing? Or is it destined to become something more like nuclear fusion, destined to always be the technology of the future, never the present? In October 2019, Google made a big announcement. Google said it had achieved quantum supremacy. That's the moment when quantum computers can beat out the world's most powerful supercomputers for certain tasks.
They've demonstrated with the quantum computer that it can perform a computation in seconds what would take the world's fastest supercomputer years, thousands of years to do that same calculation. And in the field, this is known as quantum supremacy, and it's a really important milestone.
Google used a 53-qubit processor named Sycamore to complete the computation, a completely arbitrary mathematical problem with no real-world application. The Google quantum computer spit out an answer in about 200 seconds. It would have taken the world's fastest computer around 10,000 years to come up with a solution, according to Google scientists. With that, Google claimed it had won the race to quantum supremacy. But IBM had an issue with the findings. Yes. IBM, the storied tech company that helped usher in giant mainframes and personal computing, it's a major player in quantum computing. IBM said one of its massive supercomputer networks, this one at the Oak Ridge National Laboratories in Tennessee, could simulate a quantum computer and theoretically solve the same problem in a matter of days, not the 10,000 years that Google had claimed. Either way, it was a huge milestone for quantum computers, and Silicon Valley is taking. By 2019, private investors have backed at least 52 quantum technology companies around the world since 2012, according to an analysis by Nature. Many of them were spun out of research teams at universities. In 2017 and 2018, companies received at least $450 million in private funding, more than 4 times the funding from the previous 2 years. That's nowhere near the amount of funding going into a field like artificial intelligence. About $9.3 billion worth of venture capital money poured into AI firms in 2018. But the growth in quantum computing funding is happening quickly for an industry without a real application yet.
It is not easy to figure out how to actually use a quantum computer to do something useful, right? So nature gives you this very, very bizarre hammer in the form of this interference effect among all of these amplitudes, right? And it's up to us as quantum computer scientists to figure out what nails that hammer can hit.
That's leading to some backlash against the hype and concern that quantum computing could soon become a bubble and then dry up just as fast if progress stalls. Quantum computers are also notoriously fickle. They need tightly controlled environments to operate in. Changes in nearby temperatures and electromagnetic waves can cause them to mess up. And then there's the temperature of the quantum chips themselves. They need to be kept at temperatures colder than interstellar space, close to absolute zero. One of the central tenets of quantum physics is called superposition. That means a subatomic particle, like an electron, can exist in 2 different states at the same time. It was, and still is, super hard for normal computers to simulate quantum mechanics because of superposition.
Now, it was only in the early 80s that a few physicists, such as Richard Feynman, had the amazing suggestion that if nature is giving us that computational lemon, well, why not make it into lemonade?
You've probably heard or read this explanation of how a quantum computer works. Regular or classical computers run on bits. Bits can either be a 1 or a 0. Quantum computers, on the other hand, run on quantum bits, or qubits. Qubits can be either 1 or 0, or both, or a combination of the two at the same time. That's not wrong per se, but it only scratches the surface according to Scott Aronson, who teaches computer science and quantum computing at the University of Texas in Austin. We asked him to explain how quantum computing actually works.
Well, let me start with this. You never hear your weather forecaster say, well, there's a negative 30% chance of rain tomorrow, right? That would just be nonsense, right? The chance of something happening is always between 0% and 100%. Okay, but now quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
The goal for quantum computers is to make sure the amplitudes leading to wrong answers cancel each other out, and that scientists reading the output of the quantum computers are left with amplitudes leading to the right answer of whatever problem they're trying to solve. So, what does a quantum computer look like in the real world? The quantum computers developed by companies such as Google, IBM, and Rigetti were all made using a process called superconducting.
Okay, and this is where you have a chip the size of an ordinary computer chip, and you have little coils of wire in the chip, which are actually quite enormous by the standards of qubits. They're nearly big enough to see with the naked eye. Okay, but you can have two different quantum states of current that are flowing through these coils that correspond to a 0 or a 1. And of course, you can also have superpositions of the two. Now, the coils can interact with each other via something called Josephson junctions. Okay, so they're laid out in roughly a rectangular array, and the nearby ones can talk to each other and thereby, generate these very complicated states, what we call entangled states, which is one of the essentials of quantum computing. And the way that the qubits interact with each other is fully programmable. Okay, so you can send electrical signals to the chip to say which qubits should interact with each other ones at which time. Now, in order for this to work, the whole chip is placed in a dilution refrigerator that's the size of a closet, roughly, and it cools it to about 1/100th of a degree above absolute zero. That's where you get the superconductivity that allows these bits to briefly behave as qubits.
At IBM's research lab in Yorktown Heights, New York, the big tech company houses several quantum computers already hooked up to the cloud. Corporate clients such as Goldman Sachs and JP Morgan are part of IBM's Q network, where they can experiment with the quantum machines and their programming language. So far, it's a way for companies to get used to quantum computing rather than make money from it. Quantum computers need exponentially more qubits before they start doing anything useful. IBM recently unveiled a 53-qubit computer, the same size as Google's Sycamore processor.
We think we're actually going to need tens of thousands, hundreds of thousands of qubits to get to real business problems. So you can see we need quite a lot of advances, and doubling every year, or perhaps even a little faster, is what we need to get us there. That's why it's 10 years out, at least.
Quantum computing would need to see some big advances between then and now, bigger advances than what occurred during the timeline of classical computing and Moore's Law.
Oh, we need better than Moore's Law. Moore's Law was doubling every 2 years. We're talking doubling every year, with occasionally some really big jumps.
So once quantum computers become useful, what can they do? Scientists first came up with the idea for quantum computers as a way to better simulate quantum mechanics. That's still the main purpose for them, and it also holds the most money-making potential.
So one example is the caffeine molecule. Now, if you're like me, you've probably ingested billions or trillions of caffeine molecules so far today. Now, if computers are really that good, right, really that powerful, and we have these tremendous supercomputers that are out there, we should be able to really take a molecule and represent it exactly in a computer. And this would be great for many fields: healthcare, pharmaceuticals, creating new materials, creating new flavorings, right? anywhere where molecules are in play. So if we just start with this basic idea of caffeine, it turns out it's absolutely impossible to represent one simple little caffeine molecule in a classical computer, because the amount of information you would need to represent it, the number of zeros and ones you would need, is around 10 to the 48th. The number of atoms on the Earth are about 10 to 100 times that number. So in the worst case, one caffeine molecule could use 10% of all the atoms in the Earth, just for storage. That's never going to happen. However, if we have a quantum computer with 160 qubits, and this is a model of a 50-qubit machine behind me, you can kind of figure, well, if we make good progress, eventually we'll get up to 160 good qubits. It looks like we'll be able to do something with caffeine on a quantum computer, and it's never going to be possible on a classical computer.
Another potential use comes from Wall Street: complex risk analysis and economic forecasting. Quantum computing also has big potential for portfolio optimization. Perhaps the biggest business opportunity out of quantum computing in the short term is simply preparing for the widespread use of them. Companies and governments are already attempting to quantum-proof their most sensitive data and secrets. In 1994, a scientist at Bell Labs named Peter Shor came up with an algorithm that proved quantum computers could factor huge numbers much more quickly than their classical counterparts. That also means quantum computers, if powerful and efficient enough, could theoretically break RSA encryption. RSA is the type of encryption that underpins the entire internet. Quantum computers, the way they're built now, would need millions of qubits to crack RSA cryptography. But that milestone could be 20 or 30 years away, and governments and companies are beginning to get ready for it.
You know, for a lot of people that doesn't matter. But for example, for health records, if health records could be opened up, that could compromise all kinds of things: government communications, banking records, sometimes even banking records from decades ago contain important information that we don't want to expose. So the problem we've got is we don't really know when quantum computers will be able to do this, or even if we'll ever build one big enough to do this. But what we do know is if you don't update your cryptography now, all the messages that you send over the next few years, the ones you in history, could potentially be read. What this means is, for example, if you're a Cisco selling networking equipment, you're going to need to offer quantum-safe encryption as an option in the very near future. Because even though it doesn't look like we need it right away, if your product doesn't have it and your competitor does, guess which product gets bought?
One big issue facing quantum computing, other than increasing the number of qubits while keeping things stable, is that no one actually knows the best way to build a quantum computer yet. The quantum computers that Google and IBM and other companies show off are very much still experiments. There's also a big education gap. Not many people are studying quantum computing yet. China is pouring billions into quantum computing education, and the US Congress passed a law in 2018 called the National Quantum Initiative Act in order to help catch up.
Quantum computing capable people will be a rare commodity, which means that you want to invest in them now. You want to be hiring people with quantum computing knowledge, not necessarily to do quantum computing, but because you want that intelligence in your organization so that you can take advantage of it when it shows up. Now, China, with its promise to put $10 billion in, is really upping the stakes in terms of the number of Chinese quantum physics PhDs that are going to start appearing. And you know, if that hair restoration or life extension drug happened to be property of the Chinese government, what does that do to the world economy? That's much more powerful than making war.
Other experts have compared Google's announcement to Sputnik, the Soviet satellite launched into orbit in 1957. The beach ball-sized satellite was the first man-made object to orbit the Earth. But Sputnik didn't really do anything useful, other than prove launching something into space was possible.
So with this, we have completed our journey of the quantum robots. So we can say the quantum robots are future of the next generation. So it will replace the classical robots So quantum robots can be used as a patrol warriors in military affairs and national defense. It can be used as a Mars detector and moon vehicles. It can be used as a molecule scale medicine robots. So the quantum robot injected into the body move along with the blood circulation and detect the pathological change in the body. So these quantum robots can also be used in physics, experiment of physics and chemistry and another engineering wings. If you have any query or question, then please tell me.
Okay, yes, thank you, sir. It was a very interactive session. So first query we have is difference between simple computing and quantum computing. Which one would be better in terms of security?
In classical computer, we use the single bits. Okay, but in quantum computing, we use the qubits, and qubits can be represented as superposition states. So the quantum computing provide a quantum parallelism. That means the quantum computers are better than classical computer in any terms of computing, whether it is security or computationals or any processing such as artificial intelligence or machine learning. Okay, or there are a new area upcoming in research which is called as a post-quantum cryptography. So the classical cryptography will be beat when there is a quantum computers.
Okay, sir. Thank you. Next question we have, is there any short-term course available for quantum computing?
There are a lot of courses in foreign universities, such as in MIT and another universities. But in India, we are planning artificial intelligence and machine learning in quantum computing. Okay, that a PGDC type diploma we will start in our university in upcoming years. And in MTech, I have plotted a course on quantum information and computing at Central University of Punjab.
Okay, sir. Thank you so much.
Sir, one question received at a YouTube channel.
Yes,
it is a live stream. The audience asked there, what is the use of quantum sensor?
Okay. Actually, when we talking about the robotics, to improve, I have already discussed there are two major things. First is to reduce the size of robots, and second one is to increase the intelligence in robots. Okay, and when we reduce the size, physical size of any robots, it will quantum effect will be prominent. Okay, but when we want to increase the intelligence of any robot, there are two things. We can improve using the different algorithm, or we can improve the actuators and sensors. So if we use the quantum sensors in any robots, not only quantum robots, if we use the quantum sensor in classical robot, it will also provide a better sensing power than the classical sensors.
Okay, sir. Thank you so much. So there is no more queries. Thank you so much, sir, for your kind presence, and you explained it very well in very graceful manner. Thank you so much.
Okay, thank to all the organization committee and the principal sir and activity sir. Thank you again.
Thank you.
Dear participant, we will post the attendance link in a WhatsApp group, to kindly mark your attendance. And we will start our next session at 2 p.m. It will be delivered by a Professor B.S. Pavla from NITR. Thank you all.
Okay, thank you, Pankaj sir.